Good afternoon. And let me introduce today's speaker. We are very pleased to have Dr. Matthew Partridge with us today. He's a senior research fellow at the School of Chemistry and Chemical Engineering at the University of Southampton. His research combines chemistry, physics, and biology with a focus on applied and analytical systems. Since the start of this year, Matthew has been leading the work on physical chemistry properties data collection, abbreviated as PCHPROP, as part of the PSDI initiative. His team works to make sure scientific data is accurate and reliable, something that is essential for a good research. In this talk, Matthew will take us through the data auditing process, showing how quality checks can uncover surprising mistakes in well-known data sets and why checking data carefully is so important for trustworthy science. Outside of research, Matthew is also known for his Errand Science website, a clever and funny website full of cartoons about life in science and research. If you haven't seen it yet, it's worth a look after this session. Please join me welcoming Dr. Matthew Partridge. Over to you, Matthew.
Thank you very much, Mansoor, and thank you everyone for joining me for today's webinar. So today I'm giving a webinar about a portion of my work, and the webinar title is "We Can Only Have Good Science If We Have Good Data." And today I'm talking about the data. That's my thing. Mansoor's already introduced me, so I won't repeat that. But one thing I will do is I just want to spend a brief moment explaining what PSDI is. Just for anyone who's joining us who isn't well aware of PSDI, it's a UK funded project from the Digital Research Infrastructure theme at EPSRC. And the whole idea is it's meant to build the physical sciences data infrastructure. And there's kind of many aspects to that. This is by far the densest slide I have, so I'm not going to kind of read them all out. But not only is it many aspects to it, there are also many partners. PSDI is made up of well more than 20 different partners who are collaborating behind this project to produce better data infrastructure in lots and lots of different ways and provide all sorts of different services. So please, after the webinar, go have a look at the PSDI website, because not only are there loads of services, they're also brilliantly documented and very clear with guidance documents and knowledge bases and everything. So please go check that out afterwards. But the part of PSDI that I work on, and the part that I'm talking to you about today, is the building data collections part. So part of the data infrastructure is maintaining and building and looking after and curating data collections, big piles of physical sciences data. And essentially that kind of breaks down into sort of four kind of categories of work that we do. Part of it is building robust data and robust sort of foundations for data, methods, managing data sets. Some of it is taking other people's data sets and then putting them into those robust data sets and combining them and merging them together into repositories. Curating that data for modeling so that it's more accessible, more FAIR compliant, more machine learning compliant. And finally, demonstrating it through kind of case studies. This is what we did so that other people can go and do the same. It's about kind of demonstrating best practice for these data collections. And my talk today kind of goes through all of this. It covers all of these things in sort of small ways. I'm not going to dwell too much on all of these individual areas, because as we go through, you'll kind of see how that kind of comes together. But I wanted to show this slide as a kind of a good overview for what building data collections means for PSDI, and all of the things that we kind of have in mind while we're sort of building them up and thinking about them and trying to have better data collections and have better data as a sort of a UK infrastructure. Today, I'm going to talk to you not just sort of holistically about data collections and all the data collections we have, because there are well over 20 data collections inside PSDI. I'm just going to talk today about one data collection, which Mansoor mentioned, which I manage, called the Physical Chemistry Properties Data Collection, also known as PCHPROP. I quite like the acronym. It's very natty and also goes with a really good peach emoji when I use it in documents, which people frown at in professional circles, but they just need to get with the times. The Physical Chemistry Property Data Collection is a data collection of, including the title, physical chemistry properties. And so for people coming sort of from surrounding areas of physical sciences, Those physical chemistry properties are broadly summed up by this lovely diagram that one of our senior team put together, Professor Frey. These are all different kinds of physical chemistry properties of molecules and materials. Things like their melting point, their boiling point, solubility, miscibility, HLC, vaporization constants, all of those things, all of those are properties of materials. And so this collection is trying to put together all of those properties and all of the numbers and conditions for those properties into one place so that we can do better modeling and so that we can understand physical chemistry better. And to do that, we have brought together a large number of data sources, which we've gone out and asked for, but in the vast majority of cases where we've been given those by researchers who have data sets for individual parts of this diagram and have provided them to us. So to augment what I've got on the screen, you can see here, these are all the different data collections with their little handy titles and where they fit into this diagram, what they cover. And so in total, we've got 2 or 3 for vaporization, 2 or 4 for melting points, a bunch for boiling points, 2 for miscibility, and 1 for Henry law constants. And the start of this project was to take all of these disparate data sets and smash them together into one useful collection. And that took auditing, it took care, it took time, it took thought. And we went through version 1, which got published online and is available now. And version 1 incorporated 6 of those data sources that we took through our sort of data auditing process. And that was sort of the 6 data sources. And that was the kind of version 1 of PeachProp that is available online now. And those are the ones that passed the data auditing that I'm about to go through and what we view as good data. So version 1, this lovely infographic sums up, is made up of about 110,000 unique compounds, each one described with about 23 metadata fields from those 9 different sources from the previous slide, and they cover 5 different properties at this point. So we've got data on melting points, boiling points, aqueous solubility, HL constants, and miscibility. And some of them overlap, some of them have multiple values, all sorts of different things going on there. But we've brought them all together into one database. And I won't show you the actual database because unless you're really into SQL tables, it won't really mean very much. But essentially, the project has been to combine lots of disparate data sets, make sure we've got good data, and put them into one gold standard, reliable data collection that people can use for machine learning, AI modeling, and other reasons. And the biggest part of that for us is not the practicalities of it, not the sort of the data side of it in terms of where to host a database, but it has been that checking for good data. And that's what I'm going to talk to you about today. I'm going to go through how we did that. So the aim of when we're looking for good data is that we want reliable, traceable, usable, consistent data. That's what we want. We want the data to be only those 4 things. If you list them as 4 things, it sounds incredibly easy, but obviously they all have a lot of complexity behind them. And essentially, we call this data auditing. I referred to that already. When we're kind of going through our data sets and data collections that are coming into us, we audit those data sets. That's what we are doing. And our audit process relies on us asking 3 really important questions of every bit of data that comes in and we might include into the data collection. What is the source of the data? What can we use this data? And then is the data complete and understood? So those are the kind of the 3 key questions that we go through, and each one of those has some nuance and complexity, and some of them take a lot longer than others. And I'm going to use this talk to explain to you why those are very important, not just for us. The example I'm using is of PeachProp, but these should be vital questions anybody asks whenever they are looking at a data set or a data collection from another source and using it in their experiments, or if they've got a data set that they want other people to use, they should be able to help others answer these questions really cleanly and clearly so that their data set could be more useful to others. Now, at this point, I just want to briefly take a slight side shoot because I just want to make it clear that auditing like this is not peer review. Those are 2 very different processes. And just to kind of dig into that a little bit further. So peer review is looking at the scientific merit, the originality of the research. It's looking at understanding the quality of the data that's published before it's published and reviewing it. Auditing is about checking the compliance against predefined standards and procedures after publication. They aren't the same thing. Peer reviewers are always subject matter experts. They are always looking at things in the context of that very, very specific, possibly very narrow niche area. Auditors aren't always fully domain specialists. They're focused on all of the standards and all of the things that we've set out for a data collection. Sometimes there are domain-specific things we need to think about, but generally speaking, they don't need to be domain specialists in the same way. They're not judging the quality of the source in the same way peer review would. Because peer review is trying to improve scholarly output. It wants the output of scholarly research to get better and better, whereas auditing is all about the output has happened. We now want to make that output and maintain that output at as high a quality as possible. And that's what this whole process is seeking to do. It's maintaining and trying to ensure that the quality of scholarly output is the best it can be once it's gone through the peer review process and come out. So back to our questions. First question, if you remember from 2 slides ago, what is the source of this data? So that's normally the first thing we come to. These are sort of in order of the process at which we go through. And within that question, there's obviously little sub-questions, but what is the source of this data? Or also, who gave it to us? Or where did we find it on the internet? Where was that from? We need to make sure we understand that. We need to get the sort of the names, the people who paid for it sometimes, the funders, things like that. If we can understand that, that's quite important for a lot of reasons. That kind of goes hand in hand with where it was published, because that can be very important later when it comes to rights and things like that. And added to that is the sort of sub-question, where was it first published? Because the other thing that can sometimes happen with data sets is that they are repeatedly published. And it's important to always go back to the first publication to avoid sort of Chinese whispers, and also, again, to avoid rights issues, which I'll talk about more in a minute. And then the last kind of important point about source is what method was used to generate the data. So again, that changes a bit depending on your data collection about how much you want to note that down and how much detail, but that sort of things you would agree up front. But it's always very important to understand, for example, is it experimental data or is it model data? Not every paper is always very clear about those things. That's quite fundamental. Then it comes down to what technique was used to produce it, what model was used to produce it, and all of those things you should understand those before we kind of go any further. But to give you kind of an example of the importance of this, again, I'm going to go back to PeachProp and a data source that came into us. So this was a data source called Kwai from 1994. I apologize if I garbled that name. And that came to us, this data set came to us as an email from one of the co-authors, and it came to us as a lovely CSV file, which is helpful, but essentially that is just a table full of data. This is taken from the first few lines of that data file, and that was kind of it. We got a little email that said, I think you should include this in your data collection. Here is a whole bunch of boiling points. There are some issues with this, but essentially that's not enough. Like, having it from a co-author is great, but we do need the published source. Luckily, the name of the data, and we knew who the co-author was. We could just ask them for the DOI, so that was at least quick and simple. And they sent us to their paper, which was from 1994, and it was using a neural network to determine boiling points, but they published a large number of experimental boiling points because we only take experimental data. And we looked through and we found that the table of experimental data, they didn't actually produce. They didn't make those. They were actually taken from a previous paper. So while it's the source of where we were provided the data with, it is not the source of the data. The source of the data is from the paper before. Here is the paper before, a comparative study of molecular descriptors derived from distance matrix. Wouldn't have expected melting points, but there we are. And if we go through that paper and we find again a very similar looking table of melting points, and unfortunately again a reference to where they got that from, because they didn't actually make that data. They got it from this reference from 1947, which better. So we go to the next paper, and the next paper is the structural determination of paraffin boiling points. that sounds really encouraging because that sounds like they actually did it. And we want the experimental data. We want the original stuff. Unfortunately, this won't be much of a surprise for anyone who understands how patterns work. But we checked their table, and their table also had a reference to where they got the data because they didn't take it. They got the reference from an American Petroleum Institute research project, number 44, which sounds slightly sinister. But it's okay. We found the book that came from. Here is the book that came from. And this is the final stop in the journey. There's no references from here. The Project 44 they really did do measurements of boiling points and put them into a giant book-like table. It's a thing of absolute typed beauty. And sure enough, here is in different units, but here is the melting points of the things. Now there is still a however, because the problem here is there isn't another journal after this. There isn't another paper after this. But unfortunately, here is the values that we had in the data set. The methane, the methane, the propane, the butane, that's what we had in the data set. But the values from the American Petroleum Institute only match 2 of them. One of them is 3 degrees, 2.5 degrees out. And then ethane is just completely missing from our data set, but it's in this data set. So while this is the source of propane and butane, it is not the source of methane and ethane, that data. And we have no idea where in that chain that data came from. All of those journals, just if you follow them one to another, say it came from here, but it didn't. Those values come from somewhere else. So in that data source, we can say that propane and butane, we know the source of those values, but we do not know the source of methane and ethane. And so those values are uncorroborated. They're technically sort of unpublished in that way. And that makes things like this very, very difficult to track down. And every particular property and every particular journal can have versions of that story. This is by far the most extreme, where we had to go 4 or 5 papers deep to find out that the data wasn't quite what they said it was. Generally speaking, things are a little bit better than that. But it gets more complicated the more sources you have. So these are our solubility sources, and all of them have been published at various different times, but some of them are data collections of their own right, as well as adding in new data, and they've used each other to bulk out their collections. And so if you kind of merge them together, you get a diagram that looks a little bit like this. And that's where you've got overlapping data. So the Aquasol database draws on data from numerous other sources. And we have to try and unpick what is just a duplicate of some original piece of data. And so when we do data ingest from all of our sources, we do something called overlap checking, which is to make sure that the data that goes into the data collection doesn't overlap with other data sets that have already been imported. Because if we say have 5 values for a particular melting point, but 4 of them are just the same value that we have imported from 4 different sources, and there's only then 2 values that are actually new experimental values. But that would skew a model. A model would think that those 4 values have more weight than that one. So we need to make sure that when we import data, we're importing unique data, not just copied data, because that will impact AI and machine learning modeling. So for that, when we do importing, we use sort of an overlap categorization system where we categorize data into 3 possible categories, well, technically 4, because one of them is it doesn't overlap, but 3 possible overlap categories: highly probable, probable, and possible. Highly probable is where we've got data entries where the molecular ID matches, the source matches, because we sometimes get line-by-line references, and they may all say the same source, and there's an identical value. So we know, because it's telling us that it's coming from the same source, we know that that's highly probable that that is exact overlap. Probable is where we've got matching IDs, matching values, but we don't know if the reference is right. And then possible is where the value is right within rounding, because that's the other thing we see is when one source takes their data in, takes new data in, they round that data very unhelpfully, removing some decimal places. And so at that one, we tag that as possible. And it makes for something when we do the output, it makes for diagrams like this, which are chord diagrams. And I won't bother explaining it, but essentially every bit of the pie chart around the outside is a different data set, and the lines in between are the overlapping data sets. And we know that both from the literature and from doing analysis like this, that one data set in particular got copied multiple times across multiple places. And so we've been able to not use those duplicates to ensure that we have the highest quality of data. And so this is just for solubility, but we do the same with the melting points, boiling points, and all of the other properties that we import from. There are certain criteria we have to apply to these and boundaries, and sometimes it's a bit of a discussion about whether or not possibles should be included. But what we often do is include them, but with notes, to ensure that when people do modeling, they get the option of selecting the level of scrutiny they want to apply to things like this. But even once we've decided which data we can import into our collection and which data we can look at and which data we think is good enough to look at it from a source point of view, we then have the problem of, can we use this data? So understanding the sources is the first step, because understanding the sources tells us whether or not we can use this data most of the time. Because everyone should always remember that just because the data is online doesn't give us free use. That's not how copyright works. That's not how rights work to data. There's a difference between academic fair use. So if you see data online and then download it and then use it in your experiment or compare it to your model, that's fair use. But if we were to take that data, or you were to take that data and republish it or put it into a data collection where it was republished, that is a different usage right, and that has to be understood and made sense of. Older works, sort of pre-2000, rarely have licensing information. They're just published, and sometimes the publisher will have a bit of information, but normally we have to go and ask people for permission. Some work now is often done with CC0 or just CC licenses. CC0 is the best because it basically means you can do whatever you like with it. And a lot of work is now published, particularly UK publicly funded work, under CC0. And that's the thing to look for if you are likely to republish the data. And that's what we look for. And also, if you are making data, please publish it under CC0. It makes my life a lot easier when building useful collections for physical scientists. But when in doubt, we email the originating authors, because at the very least, we want their consent. We can argue with publishers when eventually they get to us, but it's their consent we go for first. But that's using data is just about the little rights access. So while it's incredibly important and it kind of can stop us going further with some data sets, it's very important to do before we take it too much further, because it can be a real, that can be make or break. We might just not be able to use that. And it's especially important because the next step is a biggie. The next step is this data complete and understood? Now, this is where we kind of look at the data and try to understand how it will fit into the collection and whether or not that it's got sufficient quality and sufficient knowledge around it to be able to be incorporated in a way that is of high quality and we can certify good. And at this point, details matter. Details really matter, and often details are things that you have to sit down and talk about first. Every subject has its own specific details. Because we've got a broad collection across many different properties, we've had to have very subject-specific discussions in every sort of property that we're doing. And it's important to understand exactly what it is in each property that we have to be worried about, or if there's domain-specific issues that we should know about in advance. I'll kind of talk a bit more about those in a minute. It isn't always possible to capture everything, but if you plan it and think about it, that will get you through the worst of it most of the time when you're kind of putting together these collections. Key considerations is things like experimental conditions, outliers, accidental replicates, or missing values. Those are sort of things that we're really looking for to make sure that when we put them in the collection, they are really, really good. And if you're producing a collection, you should have some way of avoiding all of those problems. The first step in is the data complete and understood is really looking at the metadata. Specifically, sort of, we break it into kind of two kinds of metadata. We've got the data set metadata. So this describes the data about the data files, the kind of the containing folder or the container that has all the files. So sometimes it's just one file, but it's the metadata of just that one file, the sort of the surrounding bit. And we want from this a relatively small amount of metadata. We want to make sure we've done the author and the source. I've covered that. We want to know the date that it was produced, and we want to know the format and the data format that it's being supplied in. We get a lot of different formats. Mostly it's CSV. Some things we've got quite a lot of Fortran-based data. We've got a bit of HTML data, but it comes in all shapes and sizes. But we have to know what it is before we start, because that changes the processing. And it does, as I say, it helps with that ingest and that tracking. We never remove metadata. We always maintain the metadata. Even once individual entries are in the collection, we make sure it's traceable back to the original kind of set metadata, because again, that's very important, as I'll discuss later. After data set metadata, you've got data metadata, which is describing data about individual data. So this is, if you imagine the data set is the file and its long list of rows, all the things, the data metadata is a metadata of one row. We are looking for whether or not we have enough data about that one row entry of that one value in order for it to be considered good data. And so generally we require it to have things like a molecular ID. Different types are acceptable. A value, fairly obviously, we need a property, and we need a unit. Often the unit is not in the data set, it is within the paper, but that's also acceptable. We want more descriptors, we want more conditions, but we can live without those most of the time. Again, we never remove metadata. To give you some examples, so this is an example of one of the kind of the most rich metadata we've ever got. So these are the headings that we got from a file. And for every row, essentially, we have all of these, including error, which we don't often get. And that is brilliant for this solubility data. So really, really useful stuff. We don't always get this much metadata. We had one solubility source that gave us a few less, and we had another solubility source that gave us literally two columns. At a bare minimum, that is acceptable, because using the paper we can get to more metadata, but that is the sort of different collection, different data sets. So if you're producing data sets, for all that is I can think of, please do the first one. That would be amazing. It makes my life infinitely easier, and it makes it easier for other people to use your data in the future. It helps with understanding. To do that kind of metadata work, we use a scoring system. So because we have to check things line by line, and our metadata scoring system is to quantify each metadata for every row in the data set. And we do this partly for traceability, and partly because it makes it easy for us to very quickly find significant problems. So we essentially score every row of our data between about 0 and 12, and we classify those data sets based on how well they're scoring and how much kind of information. And by scoring it, it does help us with transparency, because we can just very quickly explain the quality of a particular data set and tag it. We can drill down into the details, but it gives us a very quick overview so that we can say this was good quality, this was not so good quality. This is the kind of the scoring system, and we score it in 5 different ways, with the identity, the units, the experimental conditions, source, and the measuring details. And we give different points depending on what they've got. So if you include inch keys, you get +4 points. If you only have a smile string, only 3 points for you. If it's a name, it's only 2 points, although we may need to lower that, because the name often is not always useful, because there's so many different variants sometimes of naming conventions, and it causes problems. Anyway. But yeah, so all of these give different scores for different things. Some of them are deal breakers. If we have no unit for the property, even from the paper, we obviously can't use that data set. But the scoring system gives us a pretty good idea very quickly of how that is. And we apply this line by line. So here is the top of the boiling point set that we started talking about. And this is just showing that the scoring is different. So we don't know the source of the second value. I should just say we don't know the source of the first value, actually. So that's not quite right. And those scores are lower. They're 5 instead of 7s. And so we know that those values aren't good. And so we could choose not to incorporate those values. We'll include the higher values, particularly because we can't trace the source. There's no fixing that. It's not a resolvable problem. And so that helps us, again, to go through our data sets fairly well. So that's the metadata side of things, and the data about the data. Then we have the kind of the picking apart the actual data, and understanding if that data itself is good quality. And this is sort of a bit more nuanced depending on the source. And I've got a couple of examples, but I don't want to dig in too deep because every source has its own unique little history of what's good and what's bad data. But the sort of things we're looking for is impossible values, examples, things like melting points that are higher than boiling points, values of zero. I don't think any of our properties have a reasonable value being zero. Unresolved DOIs, that's where we've got a value for a reference, but it doesn't go anywhere. It's gobbledygook. Or impossible ID strings, where we've got smile strings or inchy keys that are corrupted and we can't verify them. And so that's a good example of impossible data. And we have seen all of those things and have had to make sure we've built tools to constantly be looking for those. We also have values that probably need deeper investigation. So we have things like decimal misplacement. So where we've, instead of got 1.32, which would be the sort of reasonable value for that, we have 132. Now, it's likely that that is a transcription error or an error in the software that's getting the data, but it's something we have to go back through and perhaps consider manually changing. We can't have we might not want to throw that data away, but we can use it, but with notes to say we've made that manual change. The other thing we get is stuff like we get O instead of zero. And which is visually hard to see, but when you feed it into a database which is looking for floats or integers, it will immediately produce an NA value, and all of a sudden your value of 0.23 will turn into NA, and the data is lost on going into the database. And so it's things like that where we have to make sure that we've not accidentally fed in a text string into where it's looking for a number string. And again, thanks to some of our data being scanned in from PDFs and then copied, that sort of transcription error, it's not common, but it is something that does happen. Value factors different to an existing collection. So this is where we might have a value for a melting point that is, the melting point is 3000, but the melting point for the other data sets that we've imported all report the melting point to be around 300. Again, it's likely to be a human error, not an actual measurement value of 3000. We had one melting point that we were trying to import that was melted at several times the temperature of the sun, which was not right. So it happens, and we have to make sure that when we're doing that, to ensure that the data is of good quality, we find those values, either remove them or correct them, or find corrected sources, or add notes to ensure that people who are using the collection can pick that apart themselves. It's the sort of thing that can throw off an AI or throw off a machine learning model if we're not careful. And then lastly is blank entries, which, if you haven't done all of the things I've just listed and other people have already put it through an intake for a computer system or into a database, they may end up with those blank entries. So they may have all the IDs, but then no entry. And so we don't want to create entries in the system that are essentially blank. And so we need to make sure we prune that, which is easy, but often disappointing to see that there's been some data lost at some point in the process before it gets to us. To give you an example of some more domain things we need to think about, I only really want to give you, go into sort of one example, but this is an example with our solubility data set. So this is a histogram of all of the solubility in version 1 of PeachProp. And it's just showing the sort of distribution of log S values across all of the records. And you can see that the distribution isn't a sort of normal distribution. You'd expect it to be a lovely, lovely hill. And that's what you would expect log S to be. The fact that it has this kind of very strange peak and shape in the middle is concerning. So when we plotted this, we went and we looked at our data sources in more detail. So we took all 7 of our data sources and plotted their histograms. And you might be able to notice that, generally speaking, 6 of them are the sort of lovely distribution you'd expect, a sort of relatively normal distribution. And then one of them is a really giant peak. And to zoom in on that a little bit closer, here it is. It doesn't look like a normal distribution at all, not even close. That's all from one source. And it was only through communication with the author that we found out that there is actually an incredibly good scientific reason, but essentially in the experiments that they were doing, it's through a variety of kind of experimental filtering that they were looking at values in that region. So those values are somewhat pushed up against a rounding issue with the way they were running the experiment. And so we know that those values aren't correct values for solubility. They are more indicative values, or you could say that the solubility is above that value. That is not the sort of data we want in the data collection. And so when that was being imported, it didn't get past this stage. Just by looking at the data and understanding what we've got, we realized that there's nuance in the source material and the data, which we need to make sure that we don't bring into the data collection, which needs to be, available and accessible and quickly understandable. If it's, complicated data sets like this, we can point people to them, but we can't include them with too many footnotes. There's a limit to how much note taking we can do, because otherwise that puts the strain on the people who are using the data, have to constantly read very long notes with examples like this. So this data set wasn't incorporated, but to go back, all of those 6 then were, and that led us to a lovely, more expected normal distribution of solubility values. Just to kind of go through, I've gone through that quite quickly, but essentially the process we use for checking for good data starts with someone, we obviously have our data. And the very first thing we do is we check the provenance, we check the source. We want to make sure that we understand where this data came from. We want to understand that we have the right to use this data. We don't want the data to be republished or used in a way that the authors didn't think of or didn't want. We have to check that the metadata, that we understand it and that we can replicate that metadata as we continue to host the data. We want to make sure that we can classify the data set and understand exactly what sort of internal data and line by line metadata it has. We want to make sure that we've removed the outliers, we've removed some of that domain specific issues, or at least made significant enough notes that is something that is still useful in the data collection. Then we want to standardize the identifiers. I didn't really talk about this, but this is really, for anybody who's really into their inch key and smiles, there's some standardization, and particularly if you're importing smiles data from 1994, it's not the same as smiles data today. So there's some sort of historical issues as well. So we want to unify that so that it is as people expect it now. And then finally, after all of that, it goes into the data collection. And so we can ensure that the data that goes in is good data. And version 1, which I started off at, has now been migrated to version 2. It's not yet public, but here is a little brief infographic of where version 2 is looking at the moment. It's got now 400,000 unique compounds, about an additional 300,000. We've got 17 data sources. And we've also increased the number of properties. So our data collection now includes actually 7 different properties, because we now include aqueous solubility and solvent solubility. But we've also got second harmonic generation values, CMC values, critical methane concentration values, along with all of the others. So that has really boosted the value of the collection, and it's got a huge overlap of the molecules to aid for this kind of cross property modeling, which we hope that more people use it for. Now, that's where we are with it. There's one step I didn't talk about that comes now, which is auditing the audit. Now, I've kind of talked about this as I went, but I want to make a specific point about the fact that I've just obviously outlined our audit process and our checking for good quality data, but that process itself must be traceable. This presentation isn't that traceability. That traceability is making notes in every step of the audit process. Make sure we understand, some of that is where I've used numerical values or used categorizing to make it more traceable at how we've made decisions. But we have to have a documentary trail of all of the decisions that we made through that audit process and save all of those, including in the data collection. So in things that aren't actually, materials that don't make it through to the collection, we still should have the audit trail as to why they weren't included. So we end up with kind of like a data collection and then a data collection of the things that aren't in the data collection. That's all stuff that we need to document. And it's all stuff that we log as we go through this process. The reason for that partly is the transparency, and I would like to make it clear what we've done in a way that somebody can come and look through and judge and say whether or not they agree with. But also things change, audit processes change, understanding of fair data and data use and things like that changes. And we want to be able to retrospectively look back at what we've done and reassess the data in the collection and reassess the data that we didn't put in the collection. And we can then combine and reconstitute that data collection if we need to. It seems unlikely, but it's something that is an important part of future-proofing where we are with the collection and ensuring that it really has just the best quality to it. It's, you know, I can sit here and do another hour on how good I think the data collection, but it's only good if I can prove that it's good. And that's where I think auditing the audit comes in, and all of the sort of the logging and the documenting that we do. And so finally, just to wrap up, I hope you come away from this, if you're thinking about data collection or thinking about producing data in sets, is please make sure that either you always ask or that you can always easily answer in the way that you've published your data, where that data is from, what's the source of that data, whether or not you can use data or whether or not other people can use your data, how well you've typified the data and understood its completeness, and whether you've checked for all those value errors and things like that. There's rarely simple answers to any of these. I've kind of made it probably seem quite simple and quite easy, but there's a lot of judgment calls. And sometimes we have to make kind of case-by-case basis for certain properties. But we keep notes, we write stuff down, we document, and we, you know, publish how we do these things. And like anything in science, it's up for debate and for question. And I hope our collection is, you know, clearly verifiable and considered a very high quality, good source of this data and this information. And with that, I will say thank you for spending the time to kind of hear about PeachProp and hear about the way we kind of put it together. I hope it's been inspiring and interesting. I'm more than happy to answer some questions now, but if you don't, you can always email me directly. If you want to use the data collection, particularly version 2, which isn't public, again, just email me. I'm surprisingly eager to let people use the data collection before it goes online. I just want people to enjoy it and actually make use of it. So please do get in touch.
Thank you, Matthew. That was such an engaging talk. It's clear that careful data auditing isn't just a technical step, it's a vital part of building trust in science and improving the quality of research across the board. We'll now open the floor for questions. I have a couple of questions myself. So how do you decide which errors are critical to fix versus minor issues that don't affect the overall quality of the data set?
Sorry, how do we understand this critical versus minor?
Yeah.
So some of that is, I would say, obvious, in so much as if it doesn't have units, then obviously we can't include it. Some of it is harder. Some of it is, again, a bit more of that thing. Often, if it's a property that's quite tangential to my speciality, I often go out to the authors and ask, or go out to this, and we have some domain experts here. We can talk through. We essentially have a discussion about those sort of edge cases, and then we make a call and document that. To answer one of the questions in the Q&A, yes, we do document obviously this audit process. So we have version 1. There is a case study on PSDI's website to explain what we did for version 1, which is kind of like a very, very light version of this presentation. I think I went into more depth here. But we are writing up a case study for version 2, and we're writing up a paper that will be a sort of much more detailed academic breakdown of how we went through this process, and that will be published in the next few months, just as soon as I get time to finish the draft. But all of this is being published as we go through the various stages of it.
How do you go around capturing the unique, interesting data sets in a way that is clear to the user without all the footnotes? Is that where a separate data set would be useful?
Well, it's a good question, because we want to avoid too many footnotes. There's a bit of a balance. I think it's because we keep the standard quite high for what needs to be included. So again, by demanding experimental data, not model data, that avoids some issues. And then we have to have traceability on the sources. I know other data sets would allow a lot wider mix of sources, but then include footnotes as to all of that information. We don't include footnotes for that. we include that as a sort of an audit trail. So I think we also, the way the data is provided in the version 2, there's a lovely little web interface. You type it in and it tells you the values, and then you have to kind of go deeper to see the nesting tree of references or the nesting tree of footnotes. So we don't immediately make that something that the users have to deal with. They can actually just look at the data, understand that there might be a quick footnote, they can scan it and then do what they want with it.
Another question, how much of the process could be automated versus what had to be done manually?
Yep, that's a good point. We automate a lot of it. So things like that scoring, that is automated. The highly probable possible thing, that is automated because that's a scannable thing. And then, through the scoring, that's when we move things to manual. So we can prune out things that have deal breakers. We can prune out, that can all be done automated, but it's where there's, again, getting to some of those edge cases. So for the 400,000, the amount of manual intervention we have to have is not that much. Of the 16 data sources, I think 4 of them were very long, difficult processes of double checking and triple checking a lot of metadata issues, particularly with DOIs. But in general, we try to avoid too much manual stuff, and we try to avoid those kind of making judgments too much.
Thank you. How do you assess fairness of the data collection? Is this part of this auditing process? Is the fairness of the source data also considered important?
So we don't assess the fairness of the incoming data set because in most cases they are not fair. That's part of what we're doing. We're trying to take their data set and make it fair. So we very, very much want the data collection itself to be as fair as possible. And part of the version 2 is integration with Optimade and a whole bunch of other fair compliant data tools. And so we consider that the collection is the thing that should be the fairest thing we can ever make it. Things that come into it, the fact that they're not fair, that's why we're here. We want to make it fair.
Okay, I have an interesting question. If you could go back and do this again, would you do anything differently?
Well, I've cheated on this question because I have gone back and done it again. We did version 1, and then I got to try again with version 2, broadly. I mean, version 1, there is some data in version 1 that isn't in version 2 because we have updated and improved our auditing process and had another go at it. So the answer to that question is I've already done that. I got to have another go, and it's gone great. So
Each collection would need a different standard. Is there a guidance for selecting which standard to apply depending on the type of collection being audited?
So I think I can slightly refer to PSDI as a whole for this one. So that's partly what PSDI's role is in helping people, pointing people to those standards and helping people find those standards. So if you have a data collection and you don't understand what the standard is or don't understand how to do it, I would suggest you reach out to PSDI, and we might have someone who can help you do that. That's partly the responsibility of PSDI.
Our last question, do you have a process of defining terms within the metadata data sets themselves? Basically, is this data linked to a schema or ontology? And if so, how did you develop that?
We're very lucky for 2 things. One is that we have good links with Optimade, and they have a schema for data metadata that we used. But the second part of that is we at PSDI also have someone who specializes in metadata and runs the sort of metadata for PSDI over a very large number of projects and has spent a very large amount of time designing the schema and the ontology to the best standards. We have lots of local in-house expertise specifically to do that. And so that was all done prior to the collection and is being done as the collection develops. It's constantly reviewed such that we stick to that metadata schema and ontology and to the more sort of publicly accepted Optimade schemas as well.
Thank you. Thank you again for all the questions, and thank you especially, Matthew, for taking the time to address them. Just a couple of winding up things. So our PSDI resources are live. If you go to our website, you can see all the various resources which PSDI provides a range of online services to help you find, process, and learn about working with research data, including both core services and resources aimed at specific scientific communities. So Please go and take a look. And we have a couple of upcoming webinars and events coming up. Those are given in our events page. So we have ontologist workshop in Germany from 11th to 13th of November. And our next webinar in the series will be with Dr. Satya on the 27th of November. He will be sharing insights from his work on fair materials database for NMR crystallography. You can sign up. The link is available on our website. So all the webinars are posted on our YouTube channel. So our last webinar was from Dr. Samantha. It's available now on our YouTube channel. You can take a look. If you want to stay in the loop, please subscribe to our JISC emailing list. We will be sending all the updates through our emails. And that brings us to the end of today's webinar. Thank you all once again for joining us, and a very big thank you for Dr. Matthew for the excellent presentation. Wishing you all a great rest of the day and hope to see you in another PSDI event. Thank you.